And we have my whiteboard up here. So I'm going to do a couple of dimensional analysis problems first, and then we'll go on and we'll continue on with chapter 2. So I'd like to show you some techniques with the dimensional analysis problems. Okay, so here's a decent example. Now, first off, I like to set up things so that we do the entire conversion is all at one time. I don't like to do multi-step setups, but they all share some common characteristics when we're doing dimensional analysis. And I'll tell you, 9/10 of the math problems you're going to work in Chemistry 151 are going to be essentially dimensional analysis problems, but the names are going to be different. Is what's going to happen. The names will be different, but it's still, at the end of the day, it's dimensional analysis. So how about if I was to say, how many, I don't know, and let's say how many centimeters in 2.98 kilometers. Okay, now this is dimensional analysis in a sense. We're going from one set of units to another set of units, and when we go from one set of prefixes to another set of prefixes, you can go in there, and I've seen students do this, I've seen people do this where they just move the decimal point over an appropriate number of times. I'm not one of those, although I could probably figure it out. But by far the easiest way to do this is you have a series of equalities or relationships. And so what I do with this sort of thing is we start with the base unit and the prefix for both of them. So the base unit is a meter, and the prefix is centi and kilo. And if I know my prefixes, and we should memorize them, then we would say that there are 100 centimeters for every meter, and I go ahead and write this as a fraction. Conversion factors are fractions. They come from the equality 100 centimeters equals a meter, but we write it as a fraction. So I say, well, there's 100 centimeters to a meter. And kilo means there's 1,000, so that means there must be 1,000 meters for every kilometer. Okay, so I have both these relationships here. And I could have just as easily wrote it as being 10 to the minus 2 meters for every centimeter. I like to generally try to avoid these negatives up there. I mean, but it's all right. Either way, mathematically, it means the same thing. And it doesn't matter if I put kilometers on the bottom or meters on the top or meters on the bottom and kilometers top. It doesn't matter. What we're going to do is we're going to fix that with our setup, okay? And what we're going to do is we're going to take advantage of the fact that a dimensional analysis is just a big fraction. So if I had like 7 over 7, what would that be? That would be 1, right? And if I had 3.2 over 3.2, that would be 1 as well. And the same thing works with units. If you have centimeters over centimeters, well, guess what? It cancels and it's 1, okay? So we're going to take advantage of this fact, and we're going to call it canceling. So we're going to write this out as just one big fraction. And so step 1, once I've pulled down my conversion factors, 100 centimeters to a meter and 1,000 meters to a kilometer, what we do is we just draw a line. And we're going to draw another line, okay? And this is you may have seen this in high school or elsewhere, and this is just called setting up a railroad track, a track system. And basically it's just one big fraction. You got stuff on the top and stuff on the bottom. And we always start with our measured unit, our measured number. What's our measured number? Well, that's this guy right here. That's the thing you went out and measured. The 100 centimeters over a meter and 1,000 meters over a kilometer, those are our conversion factors. So we always start with the measured number. That answers the question that a lot of folks might have, which is, well, where do I start? You always start with the measured number. So we go 2.98 kilometers. Okay, that's my measured number. There it is. I got it down. And by the way, most of the time, nothing should ever live there. Okay, generally we do one measured number at a time, even when we have more than one. After this example, I'm going to show you another example where we're going to do like 2 things to 2 things. Okay, and so we have that, and now it becomes matching. So we have to match kilometers. So that kilometers cancel, just like centimeters over centimeters, we'll have kilometers over kilometers. And where do we see kilometers up here in our conversion factors? I see it right there. And so I'm going to copy that down, and I'm going to make sure that kilometers is on the bottom with the kilometers so they match. And so we're canceling. And so that's 1,000 meters. Make sure that's a 0 there. That's 1,000 meters for every kilometer. And there's an implied 1 down there with the kilometers. And so once I use a conversion factor, I like to put a check mark by it, because see, if you don't, you can actually end up reusing the unit for the conversions. Okay, so I've used kilometers, and I know I've got this set up right because kilometers cancels. Okay, kilometers cancel. So now I've used that. So now what I need is I need to be able to match up that meters, the meters on that 1,000 meters. Okay, and so the meters needs to go down here. And so that's so that meters end up canceling. And I look around, and there it is. There's my meters. Now, I've already put a check mark over that, so I'm not reusing the meters. Okay. Usually when you write down your conversion factors, you'll be forced into a particular sequence. So you don't have to memorize, the setup. And so meters is on the bottom, and I don't have to do anything to that 100 centimeters over meters. But if I had to, I could flip. If meters had been on the top, I would just flip it over. And so we say 100 centimeters for every 1 meter, and we're done with our setup. And so meters cancels. We're left with centimeters. And we can go ahead and put this in our calculator. Now, what we do is everything on top is multiplied together, and then we divide by everything on the bottom multiplied together. Now in this particular setup, there's nothing on the bottom to divide by because it's all ones. And so I'm going to go ahead and just put this in my calculator, and I go 2.98 times 1,000 times 100, and I get 298,000. 2, 3. Okay, 298,000. And now we have to do significant figures. And we go over here and we see we have 3 significant figures here. This is a defined. This is a metric relationship, so it doesn't count. Same thing over here. This is also defined, so it doesn't count as a significant figures. It's a defined metric relationship. And so our answer should have 3 sig figs. And we go, and I noticed some people had a little bit of trouble with sig figs. And so these right here, these zeros, since there's no decimal, these are trailing with no decimal. And so they don't count for sig figs. So only the 298 counts. And so we go 1, 2, 3, and we're good. It's already, so our calculator answer, coincidentally, already has 3 sig figs. So there's our answer right there. Okay, so the upshot of this dimensional analysis is you're pulling down the conversion factors you need to get, especially if you're going from one set of units to another set of units. Let's say, let's do another example here before we move on to chapter 2. Let's say I was trying to calculate, let's calculate how many miles to the gallon if a car gets, let's say, 12.4 kilometers to a liter. Okay, cars in the United States, usually we want to know how many miles per gallon we get, and cars in Europe and elsewhere, generally it's kilometers per liter is how they do it. Okay, so what I need are the conversion factors for kilometers to miles and gallons to liters. Okay, and so let me mark my spot here. And so I look back, and this is the plan. You see, I have, this is the given number that I have, the measured number is 12.4 kilometers per liter, and we're trying to go to miles to the gallon. Now, Now I learned when I was in your position that you don't generally want to try to tackle something over something to something over something to get to. And you can, but it makes it vastly more difficult. The easiest way to do this is to split out to two separate conversions. You go kilometers to miles, and then you can recombine, go from liters, oh, let me erase that. You can go from split out the liters and go liters to gallons, and then you recombine at the end to make it miles per gallon. Okay, so that's the kind of plan that one should do. Okay, and so let's do that. So we have kilometers to miles, and I look up the length, and a kilometer from the back of the book, 1 kilometer is 0.621 miles. And we'll also find out that a gallon for volume, where's gallons over here? A gallon is 3.79 liters. And I just looked these up on the back of the book, or you can Google it. Google's a pretty good resource for this as well. Actually, Google's a little bit faster, but I just looked at the back of the book. And so let's do kilometers to miles. And so we say, well, I'm going to draw a line. I'm going to draw another line. Don't need to make it very long in this case. And my measured number is 12.4 kilometers. And once again, we're going to make sure that our units can't cancel. And to do that, we need to get kilometers to match. And so this case, I need to get kilometers on the bottom. So I'm going to flip it over. And this becomes 0.621 mile per 1 kilometer. Kilometers cancel. And I've got a number that I can put in my calculator now. So I go 12.5 times 0.623. And I got 7.7875. Now, I generally don't round until the very end, so I'm just going to carry some extra digits, even though, strictly speaking, if we stop there, it would be 3 sig figs, because we have 3 over here and 3 over there. But I'm going to keep that a little bit extra for rounding purposes so that we don't end up with rounding errors. And now we'll go ahead and do the gallons. We draw another line, there we go. And in this case, it is a liter. That's what we're starting with. Over here is what our measured number. So we always start with our measured number, and that's 1 liter. Okay, and now we look over here and we see liters is already on the bottom. So we can just copy it down over here. Just copy it down, and so we say 1 gallon is 3.79 liters. And we put that in our calculator, and so we say 1 divided by 3.79, and that is 0.26, and we'll carry a couple extra digits, 0.26385. And I would say carry at least one more beyond your sig fig. So 4 or 5 digits is good if you're going for 3 sig figs. And so now what do we do? Well, what are we looking for? We're looking for miles per gallon. I have miles over gallons, and we're going to divide these two and get our final answer. And so I take the 7.7875, and I'm going to divide it by the answer. I just leave the answer in my calculator, and I get with 3 sig figs, because we want our answer to be 3 sig figs. That's our measured number, and we went all the way through. It's 29.5 miles to the gallon. And there you go. So the upshot of doing these when you have something over something is the easiest way to do it is just split them out. So you have miles per gallon. You go from kilometers to miles, and you go liters to gallons, and recombine it at the end. And generally, this is how you do conversions. Another thing, only make a quick note here, and that's going to be the two examples I do. But if you were going from, say, centimeters cubed, let's say the inches cubed, one volume to a volume, a good strategy on something like this is you might not find that relationship directly, but you do know it's 2.54 centimeters to an inch. And what you do is you just go ahead and cube everything up to get your conversion. And so if you cube everything up on the outside, the centimeters become centimeters cubed, and so you go 2.54 to the third. And so now I can produce a conversion factor of 16.4 cubic centimeters equals 1 inch cubed, and now I have a conversion. And so sometimes you have to take the basic conversion, which is 2.54 equals 1 inch, and you might have to do a little bit of extra work to get it into the proper form. And now we can go directly. So if I had so many cubic centimeters, let's say I'm trying to go from a 305 cubic inch engine on a car, well, how many cubic centimeters, how many liters that is, then at least you have that conversion that you can use. Okay? All right. So let's go ahead and continue on. And we're going to go ahead and start chapter 2. And I'm going to annotate these. Now, I'm not going to hit you with all the slides because you can read the slides yourself, but I would like to highlight some of the pieces of the slides so that you can have a little bit of perspective on it from my standpoint. So let's go ahead and start slideshow here. And let me go ahead and hit the arrow down. Now, starting with chapter 2. Chapter 2 is about atoms and such. And way back when, with Dalton, there was this gentleman named Dalton. He was English. And prior to him, there really wasn't a good understanding of what is matter. And Dalton comes along and says, you know what? Elements are composed of atoms, okay? And all atoms of a given element are identical. But each atom of an element is different from other elements. Now, a way of looking at this is to say that my carbon atoms are identical to your carbon atoms. Even though we're very different, we're different people, a carbon atom's a carbon atom, an oxygen atom's an oxygen atom, and they're all the same, okay? Well, actually not quite the same. There's things called isotopes, but this is Dalton's theory. And one thing that you can't do, and if you've ever heard of alchemy and alchemist, is you can't just change one element to another. So no lead to gold, no lead to gold. Oh, very, very sad. Okay. The alchemists were very unhappy to find that out, that no matter how hard they tried, there's no way that you're going to get gold from lead because they're both elements. They're different atoms. They're just totally different. And compounds are formed when you have two or more different elements. All right. So nitrogen and oxygen would combine to form nitrogen oxide. Now, one thing that makes an element that people get confused about is elements cannot be broken down into simpler elements. Okay, and once it's an element, you can't be broken down. All right, whereas compounds can be reduced to simpler elements. So, once you form that nitrogen oxide compound, well, you can certainly go back in the other direction and get nitrogen and oxygen atoms. But, if you have a sample of oxygen, it's all oxygen, and you don't break it down into something more simple. So keep that in mind that you can't do that. Now, do you need to memorize this? It would be a good idea that this is the sort of concepts that you would want to have a familiarity with, like with flashcards or writing it over and over again, whatever you need to do. Okay, so but this was all the very beginning of trying to understand the nature of matter. Okay. Now, law of conservation of mass is the total mass that you start out with the reaction is also going to be the same amount of mass at the very end. So what takes place in a chemical reaction, another way of saying this is that when you have a chemical reaction, you're just moving stuff around. You're just moving stuff around. So, and the law of conservation of mass is the basis for balancing equations too. If you ever wondered why in the world do we have to have balanced equations, which means the same number and type of atoms on both sides, well, this is because of the law of conservation of mass. All right, so a little bit of history here. Like I said, these slides, I don't usually do a lot of PowerPoint slides, but these slides are actually pretty good. Just to summarize a little bit of history, J.J. Thomson, he discovered the electron. He did what's called an electrical discharge tube. You can see the picture. If you put a charged plate on either side, or a magnet for that matter, you can actually bend the electrons to follow the force fields. And so he discovered that electrons were in everything. It wasn't just a characteristic of the cathode and anode, but in fact that it was a characteristic of elements themselves. And so this was back in 1897. J.J. Thomson, who actually found a few things, and electrons is one of them. And so the same J.J. Thomson, he also set up an apparatus so that he could measure the charge to mass ratio, and it is 1.76 times 10 to the 8 coulombs per gram, and that is a lot of charge. A coulomb per second is an amp. This is the same amp that you see on a circuit breaker. So many amps capacity. That's a lot of amps. If you were measuring it as current. And so it's a good number. You don't have to memorize that number. A lot of these constants you don't need to memorize. You just need to know where to find them. Millikan oil drop experiment was in the early 1900s, and this was a fellow at University of Chicago, who's a professor out there. And he was able, through the oil drop experiment, which is actually an experiment that you can actually buy an oil drop apparatus on, from a scientific supply house, and I think they run only just a couple of $100. Pretty cool experiment. You might be able to do it in physics lab. They may or may not have an oil drop experiment, but it's pretty cool. And since the mass of the oil particles and the field strength, you can actually calculate the charge of an electron. And so he determined that back in 1909. A lot of really exciting stuff was happening in the early 1900s, and this is one of them. So we have the electron. Radioactivity, that was first Henry Becquerel. He was actually a photographer. He was not a scientist. All right. And then Ernst Rutherford found some particles, and because of the nature of these particles and this disintegration of atoms, you can infer that they must be parts of the atom. And so there were three of them. You had beta rays, which actually turned out to be electrons. You have alpha particles, which turn out to be helium nuclei, and gamma rays actually has neutrons hidden in there. And because neutrons are electrically neutral, they weren't found for quite some time. And so because we have these positive and negative particles, J.J. Thomson, same guy who discovered the electron, well, he realized, and the importance of this plum pudding model is that you have this, that we already knew that atoms are electrically neutral unless you do something to them. So if you have a negative part, you better have a positive part to match up with reality. And he says, well, you know what? The negative parts, well, I already know those are particles, but they didn't know what the positive part was yet. And he says, it's just kind of like a goo. It's a goo of a positive charge matter with these negative electrons embedded into it. And so if you go by this model, if you were to shoot a particle at them, chances are you're going to hit something. If you were to shoot particles at this, okay? And so it's an idea that the atom is pretty solid. Now, any good model, you have to experimentally verify it. And then Ernst Rutherford comes along and he does something called the gold foil experiment, where you have a very thin single atom layer of gold and you shoot particles at it, which is essentially what I just described right here with the plum pudding model. Now, look, if the plum pudding model is real, then you should be scattering particles off that gold foil. And what happens is literally uh, the vast majority of it ends up going right on through like there's nothing there. And literally, these are not beam spots. They're literally spots, and this is actually a beam spot, the one that I just added on there. And the only way that's possible is if, as it goes through the gold foil, that there's nothing there, or at least whatever's there is very small. And so, sure enough, the conclusion is that atoms are actually mostly empty space, and that in the center you have a small, hard, positively charged nucleus. And that, of course, we go on later on and we discover that it's the protons and neutrons that are in the nucleus. And basically, atoms are mostly just empty space. Okay, that's mostly empty space with a small, dense nucleus in the middle. All right. And so, I'll give you an idea of how big atoms are. They are really small. An angstrom, the A with the little circle on the top, is actually 10 to the minus 10th meters. It's an old unit. It's a tenth of a nanometer, 1/10 of a nanometer, which is 10 to the minus 9. So atoms are really small, um, on the order of a tenth of a nanometer or so. And nucleus is like way, way, way smaller. It's 10 to the minus fourth. So it's a factor of 10,000 smaller than the actual volume occupied by the atoms. Okay, so that's the current general model of what atoms are, as a small dense nucleus in the middle surrounded by electrons. All right, protons were discovered in 1919. It took another 20, what is that, 20, yeah, 23 years before the neutron was discovered. And that, quite frankly, is because if it's neutrally, it's neutral. Neutrons are neutral. They don't have any charge, and so that made them particularly difficult to find. And so, but when they were discovered, the neutrons, it actually, and it's funny because there's only just one sentence in all these slides, and it's not even really mentioned too much in the textbook either. But the neutrons made everything possible. Neutrons make possible nuclear reactors. It makes possible nuclear weapons. It makes possible many things with the discovery of the neutron. That kicked off, really, truly, the discovery of the neutrons kicked off the atomic age. All right, now this table here, 2.1, there's one in your textbook very similar. You need to commit this to memory, but only in the sense that not the 1.073, but that these are practically 1, 1, and about 0. Okay, about 0. 5.4 times 10 to the minus fourth compared to 1 is approximately 0. And AMU is 1/12 the mass of a carbon-12 atom. And so you weigh out an AMU, and there's a conversion. We won't worry about it. You'll actually, if you take a Chem 152, you'll work a little bit more with actual masses. And I forget how big is an AMU. Atoms are pretty small, but you can look up the mass of an AMU. We won't mess with that. But you do need to know that a proton is positive and has a mass of about 1 AMU, atomic mass unit, and a neutron's about 1 and has no charge. An electron has a negative charge. It's the same. It's the opposite of the proton. Okay, but it's also very small. And of course, protons and neutrons are inside the atom. Electrons are on the outside. All right, now that's it for the PowerPoint. Let me go ahead and pull up my. I don't want to save that either, and we're going to go ahead and pull up my slides. Here we go. All right, and we're going to go ahead and do atomic symbols, and I'll show you how to do these appropriately, and then we'll talk about, things like weighted averages and things like that. All right, now let's go back here, start a fresh slide. Okay, so there's these things called atomic symbols. All right, now if you look on the periodic table, and I happen to have one right here. Where is it? There it is. So you'll pull up. And if you look on the periodic table, you will see all these symbols and things like C and for carbon and N for nitrogen and O for oxygen. And you look over here, see there's a carbon, you got nitrogen, oxygen, fluorine, things like that. And you'll see that each one of these is a symbol that represents the name of the element. Now, most of them, they're either going to be English derived, or some of them come from Greek words, and some of them are from the names of people. Okay, and so generally speaking, you're going to have either one letter or two letters, and the way we're going to do it is we're going to capitalize the symbol. So C is the symbol for carbon. And Ca, we go capital C, lowercase a. Well, that's calcium. And of course, H is for hydrogen. But sometimes, it kind of makes sense, C for carbon, Ca, well, calcium goes Ca and hydrogen. But you are going to run across where they're not the same, such as Na, well, that's sodium. And that comes from natrium, which I believe is Greek. And so the name and the abbreviation may not match up. Okay. And so like potassium is K, but phosphorus is P, and so forth. So the thing is, you got to make sure that you have an uppercase to start out with, and if you have two letters, you're going to go lowercase for the next one. Now, the reason why we end up with some with two letters and some with one letters is actually pretty mundane. It's because, well, there's over 100 elements and there's only 26 letters in the alphabet, so you have to start doubling up with letters. Okay, and that's why you have some that have more than one letter. Okay, now when we're trying to write out an atomic symbol, the symbol itself, if you look on the periodic table, you will see, I'll go ahead and pull up that picture. You will see that there is a number above the element on the periodic table. And if you look at carbon, you'll see there's a 6 above the carbon. And it looks just like this when it's on the periodic table. Okay, now hold on. Let me erase this, make a little box a little bit bigger. And if you look on the periodic table, you will see this for carbon. Okay, now we'll mess with the bottom number in a little bit. Well, let's just focus on the top number. That top number is what's called the atomic number. All right, and it represents the number of protons. The periodic table is organized by the number of protons. Okay, and you may say to yourself, well, what about the neutrons, and electrons? Well, they're in there. We're getting to it. Okay, so that's the atomic number, the number of protons. Now, all carbon atoms have 6 protons. If it has something other than 6, then it's something different. So we can have, say, nitrogen, which has a number over the top, and it means the number of protons as well. And nitrogen has 7 protons. Or does it? Let me make sure. Hold on. Nitrogen. Yeah, it has seven protons. Don't doubt yourself. And we look at and if you look at the periodic table, underneath nitrogen is 14.0067. More on that in a minute. Okay. Now, the bottom number represents a weighted average of all. It is a weighted average of all the isotopes, all natural isotopes. Okay. Now, I mention that because this is the atomic mass that's on the bottom. Now, when we write a nuclear symbol, which we're fixing to do, when we write an atomic symbol, we do not use this, never use, for atomic symbols. Now we're going to use that bottom number for a lot of calculations, particular when we're going to in future chapters we'll have something called the molar mass, and that's what we're going to use that for. But for atomic symbols, we would not use that bottom number. So we would not be using these bottom numbers, but we do use the atomic number. So if I was to let's write out the atomic symbol for carbon, and this is for one particular isotope. Isotopes being, well, I might as well just go ahead and write down here. Isotopes have same number protons, because after all, if it doesn't have same number protons, it's not the same element, but different number of neutrons. Okay, and so let's write out some isotopes of carbon, and we would say, now this is how we're going to do it. Now that 6 that's up there, that actually, when you're writing the symbol, it actually goes low. All right, small number goes on the bottom. Now the top number, and this is the atomic mass. The atomic number. Now there's a number up top, and that's called the atomic mass number. And it represents protons plus neutrons. Okay, it's called the atomic mass number because protons and neutrons, they come in counted quantities. You either have 1 proton, 2 protons, 3 protons, 4. Same with neutrons. You either have 1, 2, 3, 4, whatever, but it's a counted number. You don't have like half a neutron or half a proton or anything like that. It's an actual number, and you get that number by adding the protons, or the atomic number, with however many neutrons it has in it. So you can have different isotopes, but they're still all the same element. And so another common isotope would be carbon 13. And once again, it has 6 protons. And we have carbon 14, which has 6 protons as well. And if you take a look here, we can actually say, well, how many protons, how many neutrons, and we might as well just make it complete, say how many electrons if it's electrically neutral. And of course, to be electrically neutral, we have to have same number of protons, same number of electrons. So in all cases, the number of protons for each 3 of these isotopes is going to be 6. And for carbon 12, and that's how we say it, we say carbon dash 12. That means it's carbon with an atomic mass number 12. And we say, well, it has 6 neutrons, because 6 from 12, well, if you subtract off the protons from protons plus neutrons, well, what's going to be left over is the neutrons. And so if we subtract 6 from 13, we get 7 neutrons for carbon 13. If we subtract 6 from 14, we get 8 carbons for carbon 14. And so we can always find the number of neutrons by subtracting from the mass number minus the atomic number. You can always find the neutrons. Mass number minus atomic number gives you the number of neutrons. And to be electrically neutral, to be neutral, the whole atom, if it's neutral, the number of protons has to equal the number of electrons. And so 6 protons for carbon 12 means, and for carbon 13 and carbon 14 means we have 6 electrons all the way across. Okay, now, remember that 12.01 that I was showing you right up here? See, carbon, and it has 6 protons, and you may say to yourself, well, that just means it's carbon 12. Well, it's a weighted average, naturally occurring. You have these 3 isotopes here. We have carbon 12, carbon 13, and carbon 14. And it turns out that you have roughly about 99% of naturally occurring carbon is composed of carbon 12. And carbon 13 and carbon 14 are less than 1%. And so if you average these as a weighted average, in other words, you take the percent composition times the mass, and then you add them up, you will get a weighted average. And it would make sense that if you have carbon, mostly carbon 12, that you would be very close to being 12, but you're not going to be right on 12 because the mass, it's an average of all three isotopes. And so when we're doing chemical reactions, typically we have an isotopic mixture, a naturally occurring isotopic mixture. Now you can buy samples that are all carbon 12, 100% pure carbon 12, and you can buy samples that are very close to 100% of carbon 13 or carbon 14. You can. And so they wouldn't have an isotopic average. It would be just carbon 12 or whatever. Okay. And same thing happens, when we have something like chlorine. Chlorine, its weighted average mass, let me look over here and pull it up here, and its weight is 35.45. 35.45. And it turns out, I believe we have 37, chlorine 37 and chlorine 35. And so I think I don't remember the exact number, but it's something like about 2/3 is chlorine 25, and about 1/3 is chlorine 37, and this represents the average. This is what we would have on the periodic table, would be 35.45. So you have an isotopic average. It turns out there's two isotopes with chlorine, and you have some elements that have 4 isotopes naturally occurring. You have some elements which have only one. Fluorine, for instance, has one naturally occurring isotope. Fluorine, letter F, has one isotope. An isotope just meaning the same number of protons, but different number of neutrons. Okay. And so if you want to find the average, then you just look up, the isotopic abundance and add them up. And it's not a, it's a, it's an intellectual exercise, but it's not very practical. Because what you do is you just look it up. It's on the periodic table. That gives you the average. Okay. All right. So let's take a look at the periodic table and its arrangement. I'll go ahead and pull that up again. So, like I said, here is a periodic table. It has all the known elements, and they are arranged in order of atomic number. And so we start with hydrogen at the top. There it is. We start with hydrogen, and we work our way across over to helium, and we just keep going row by row, left to right, and it's organized in order of atomic number, or an order of protons. Now, originally, one of the early periodic tables actually had it organized in order by atomic mass, and that caused problems because you want them, the columns, you want the groups to have similar chemical properties. And this is where the whole idea of the periodic table came out, is that people started noticing that certain elements shared chemical properties, such as these guys over here. If you take fluorine, chlorine, bromine, or iodine, they may have different physical properties, but chemically they behave very similarly. Okay. And so if you organize this so that every line, every row repeats chemical properties from the previous one above it, you end up with this arrangement right here. Now, they didn't know when they were making the periodic table that it actually, the reason why you end up with periodic properties has to do with the electronic characteristics of the atoms. In other words, where are the electrons in the atom and their particular arrangements. Now, they don't necessarily go by increasing mass, on the other hand. Let me go ahead and blow this up for you. I want to focus in here on, where is it? It's chromium, magnesium, copper. Let's see. There are a couple of them in here where they go out of order a little bit. And so I'm trying to remember which one it was. Nickel. Yeah, here we go. If you look at cobalt and you look at nickel, then you look at copper, you'll see that going from cobalt is 58.9, and then it actually drops going to nickel. So if you were to organize the periodic table by mass, you would actually, these two guys would switch places. They would switch places between each other, and nickel would end up being over here. But nickel does not behave like rhodium, and cobalt does not behave like palladium either. Okay, chemically they behave differently. So it does go in order of increasing atomic number, and that's part of the reason why. Like I said, a long time ago, one of the first periodic tables actually had cobalt and nickel switched with each other because of the atomic mass that they were using. Okay, all right. So now, as we look at this periodic table, the thing that really is important to realize about it is that it's organized the way it is, and because of that, we end up with different groups. And so we have 1A, 2A, and then we have a bunch of B's, 3B, 4B, whatever, and then we have like 3A. So we jump from 1A to 2A, and we go all the way over here. We go 3A, 4A, 5A, 6A, 7A, 8A. And those are the group numbers. Now, these groups have some common names, and let me go ahead and show you some of the common names. And I should have just, I think what we'll do is just start over with that rather than try to erase it. Okay, so we have common names for these guys. Now, except for hydrogen, not hydrogen, these guys in group A are called the alkali metals. And group 2A is actually the alkali earth metals. All right. And those are two important groups. They have some characteristics. Generally, they're soft and extremely reactive, but they are metals. And all in here, these are your transition elements or transition metals. And finally, we have over here, we have the halogens. And then these guys over here on the last, the pink column, that's the noble gases. All right, and like I said, when they're in the same column, they share very similar chemical properties. Now, it also makes the chemistry similar. So if you know the chemistry for one, you can take advantage of that and understand the chemistry for the others. They'll behave not identically, but pretty close, pretty close. Now, commercially, this has some important implications. So if you were like trying to find, say, gold and silver, which are pretty valuable, believe it or not, if you have a copper mine, you see how these guys are all in the same group, copper, silver, and gold. If you're mining copper, well, since they're similar in chemical properties, copper, silver, and gold, believe it or not, they're similar in chemical properties. If you have a big copper mine where you're producing tons and tons of copper, as a byproduct, you will actually get some silver and gold. Probably not enough to run your copper mine as a gold mine, but enough to make a difference. So you get this bonus when you have a big copper mine and big industrial process, big trucks and big holes in the ground. And so if you have gold, if you have a copper mine, you can get some gold out of it. You sure do. And matter of fact, that's a significant source of gold in this world is from copper mines. Now, if you'll notice the yellow zigzag elements, these are called metalloids on the yellow zigzag. These are called metalloids. And what a metalloid means is like a metal. These elements actually mark the boundary between metals and non-metals. So everything to the left and down is a metal, and everything up and to the right is a non-metal. And pardon me for the color contrast on here. I don't know how to change the color of my pen just yet. And right on that diagonal, that's the transition between metals and nonmetals. And so elements like silicon and germanium and arsenic and antimony, they share characteristics that are kind of part way between metals and nonmetals. So metals conduct electricity really well. Nonmetals don't conduct electricity, and the metalloids that are running down that diagonal, well, they can sort of conduct electricity a little bit. Um, Metals you can bend really well. Metalloids you can kind of bend. They'll bend like a record. You know, you can bend them a little bit, but they break at some point. Your nonmetals don't bend at all. And so now you need to know where the metals and nonmetals are, because when we get into naming, which we'll probably do on Wednesday, if you don't know where your metals are and your nonmetals are, it's going to be very difficult to do your naming. So you need to know where they are. Now, question comes up, which elements do I need to memorize? Which ones do I need to memorize? And the answer is you don't need to necessarily memorize all of the elements on the periodic table. I mean, when I was in your position, one of the tests that I had to do, they gave me a blank periodic table, and the quiz for the day was fill out the first 3 rows. And I got it, but I'm not going to make you do that. What I am going to do is say that you need to know about where things are. So if you have a problem that you're working on and you're pressed for time, like during a test, you don't want to be hunting all over the periodic table. So you should eventually know, sodium's over here versus, say, chlorine's over there. And so you got to train your eyes to know where to look. In other words, I'm not going to look over here to try to find nitrogen because I know it's over here. Okay, that's what I mean. Train your eyes for the location. If you are practicing, and you should be practicing a lot. I've had all of you I've had for lab. And so one of the things that I've tried to emphasize early on is the importance of massive amounts of practice. And the more you practice, and you're going to need a periodic table to go with your practice and with this chapter and the next, and actually for a lot of the chapters, you will need to become familiar with where things are on the periodic table. And eventually you will. If you practice enough, it becomes second nature. Now, are you going to do problems where, maybe I need to know, where rhodium is? No, but you may very well do a lot of problems with iron, though. And there's iron. It's in the middle of the periodic table near the top. And so I'm going to leave you with this. There is one thing I do want you to memorize on this table, is the diatomics. Where are the diatomics? Diatomics, what does dia mean? Di means two. And so there are naturally occurring diatomics. And that's where, if you find them alone, but not part of a molecule, not part of a molecule, if they're part of a molecule, they can be anything you want them to be. These are your diatomics. There you go. It's these guys. It's like a flagpole right there. And hydrogen. So these guys appear as like H2, N2, O2, F2, etc., so forth. And there are 7 of them. There are 7 diatomics. Okay, there are 7 diatomics. You need to memorize the location. This is very important because you do not want to be the person who writes down a formula with a straight face. Iron plus oxygen gives me iron oxide. Okay, I'm going to show you how to do that in a little bit. But you do not want to be that person, because you will get in trouble for that. Okay, it's not O, it's O2. It's on the periodic table. It's on this flagpole. Now they're the only ones, and there's only 2 elements on this table that are liquid as well. We've got diatomics, and we got 2 elements that are liquid, and that's bromine and mercury. Those are the only 2 that are liquid. So all the rest of them, most of them are solid at room temperature. There's some that are gases at room temperature, like all your noble gases are monatomic gases. So they just appear by themselves. some of your halogens are gases as well. So there's not very many gases on this periodic table. It's mostly solids, it's mostly metals, as a matter of fact. And it is important to know that where your 7 diatomics are. Okay, so I'm going to stop there. And